Hey there, Calcsters. Welcome to your first video. Today we're going to be talking about estimating instantaneous rate of change. It's a pretty cool topic because it's a bridge between some math that we've done before that kind of introduces us to some really cool calculus. So that's what we're going to be working on. Before we begin, let's look at our learning target, which is students will be able to estimate instantaneous rate of change through average rate of change and be able to determine how a function is changing at a particular moment in time. So what I want to draw attention to is average rate of change. Hopefully that's something that is getting your mind going, something that sounds familiar because you've been working with it for a really long time. Average rate of change, that's slope. It's calculating how something is changing over a particular change in time. Now, it's been a while, so let's talk about how we calculate slope. Okay, ways that you've seen it before. You've seen change in y over change in x. You've heard rise over run. Okay. Most specifically, our slope formula, which is what we're going to be utilizing to introduce this new calculus activity, is y2 minus y1 over x2 minus x1, which is exactly the same as what we have over here, the change in y over the change in x. It's the difference between the two y values divided by the difference between the two x values. Now, when we talk about average rate of change, we're talking about a change in time that is noticeable or longer. Usually we'll say, what's the rate of change from 0 to 10 seconds? Or what is the average rate of change for the first minute something is moving? And though average rate of change is a good thing to know how to do, and it can help us describe many situations, particularly linear ones, oftentimes things don't have that constant rate of change. And so in that case, we want to be able to describe the rate of change in different places. So at an instant. So here's where this gets challenging. It's really hard to approximate an instant or use average rate of change to calculate at an instant because an instant is one moment in time, okay, one particular place. And if you look back right here, this is relying on two x values and two y values. So you might be wondering, how will we utilize this to create this estimation of instantaneous rate of change? Well, to estimate an instant, we need a really, really small change in time. The smaller the change in time, the better approximation of an instant we will have. And so what we will do is for our x values, which are going to be time because time is almost always the independent variable, we'll be using a very, very small change in x. So let's put this into practice. So let's suppose that you're walking through a door with an automatic closer, and you push it open, and then the automatic closer slowly closes it to make sure that it doesn't slam. And let's say the degrees the door is from close can be modeled by the equation d is equal to 200t times 2 to the negative 1t, where t is in seconds and d is degrees from closed. Now, if I were to do a quick sketch of that graph, 1, 2, 3, 4, 5, 6, 7, it's going to look something like this, where it opens real quickly and then slowly closes over time. Let's say that I want to know what the rate of change is, the instantaneous rate of change at 1 second. So I'm looking right around there. Now, it looks like based on my graph that it's still going up, so I would expect a positive rate of change. But let's talk about how we could find a great estimation for instantaneous rate of change. First of all, I'm going to use my slope formula. So I'm going to rewrite that over here. I've got m, which is our variable representation for slope, is equal to y2 minus y1 over x2 minus x1. So in order to use this, I'm going to need two sets of values, two x values, two y values. And I want things that are really, really close to 1 second. So if that's the case, what I'm going to do is make a table of values. And to estimate an instant, we usually say if we go as small as 1/100th of a second, that's going to be a pretty good estimation of an instant. So since I want to know what's happening at 1 second, I'm going to get a couple of values here. I'm going to look at the value at 0.99 seconds, at 1 second, and at 1.0 seconds. So I'm going to get my calculator now. I'm going to start by plugging in the equation. So 200, I'm going to use x, times 2 to the power of -1x. I'm going to set my table to start at 0.99, and I'm going to do a change in table of 0.01. And I'm going to go to my table. Now, right now, something I would recommend is for you to practice this using your calculator. So this would be a great time for you to pause the video. And go ahead and plug your equation into your graphing calculator and ensure that you can get the same values that I do on here, which I'll write down in just a moment. So here are the values that I got when I plugged the equation into my calculator and I used my table function. Notice that when I get my values, I'm taking 4 decimal places here. And I did that by arrowing over, so I was highlighting the answer, and then I got all of those decimal places to make our answer a little more accurate. Now, you might be curious, if we're doing an estimation of instantaneous rate of change, and we're using the slope formula, I said before that we need 2 values, okay? But if we want to make this a really great estimation, then we want to make sure that we do both, I'm going to call it the underestimate, which is what happens right before 1, as well as the overestimate, what happens right after 1. So I'm actually going to utilize the slope formula twice, and then I'm going to average those values together. So let's take a peek at what that looks like in practice. So this part you should be really familiar with. I'm finding the rate of change between 2 sets of values. So my first slope, which I'm doing in blue right here, I would find by doing 100 minus 99.6886 divided by 1 minus 0.99. Calculating that, I get 0.3114 divided by 0.01, which is 31.14. And that would be degrees per second. Now, like I said before, that's a great approximation, but that's what happened right before and at 1. So I want to average that with the overestimate, as I like to call it, which is what happens from 1 to 1.01. So I'll do that calculation here in yellow. Same process. This is my second slope, so I'll call it M2. I do 100.3023 minus 100 over 1.01 minus 1, which gives me 0.3023 divided by 0.01, which simplifies to 30.23, and that's degrees per second. Now, to make this the best approximation of an instant that I can, I'm going to take those 2 values and I'm going to average them together. So I've got 31.14 plus 30.23, add them together and divide by 2, which gives me 30.685. That would be degrees per second. So what that is it's telling me how fast that door is moving, okay, at 1 second into its path. Pretty cool, right? So let me summarize what just happened. What we did is we were finding an estimate of the instantaneous rate of change, utilizing average rate of change, the slope formula, something you've used for years and years. The way that we estimate that instant is by doing a really, really small change in x. And again, what we expect you to use anytime you do a calculation is a change in x of 0.01. Because 1/100 of a second is so small, we probably don't even recognize it. Pretty close to an instant. Now, we also expect that you're always going to do the two estimations and then average them together for the best estimation. And again, this is an intro to calculus. You will learn how to do it exactly in our upcoming units, but this is a great way to bridge some prior mathematics to what you're doing now. One more thing I want to mention. Let's say you're given the same scenario, but in the scenario, you're not given an equation that accurately models what's happening. But instead, you're given a table. So let's say I'm still talking about the door opening and closing ever so slowly. But instead of the equation, they give you a table. So for example, this table of values. What I want you to notice is that in this table, it's not going up by 0.01. It's going up by 0.1. But if you're being asked to make an estimation of instantaneous rate of change based on a table, you just have to use what you're given. So if I were going to do my estimation for the scenario we've talked about using this table, I would still do the slope calculation twice, but I would have to use a change in x of 0.1. So my first slope would be 100 minus 96.46 over 1 minus 0.9. My second slope would be 102.63 minus 100 over 1.1 minus 1. I would find those two values and then average them together. So just a point to mention, if you are not given the equation, but you are given a table, you just have to work with what you got. So that's all we've got for you for today. Thanks for tuning in and listening, and we look forward to digging in a little bit deeper in our live class tomorrow. Have a great day.